So hello, everybody. Welcome to second discussion for DeepRob. Today, we're going to do an introduction to what we're calling the props dataset. And that's the dataset that you'll be working with on Project 1. Hopefully, everyone saw the email that I sent out maybe like 30 minutes ago or so with a few updates. So I'll go through those administrative updates first. Before I get started, I'll just point out like all the images on this slide are from the dataset that we're going to be working with in Project 1. And so we're going to talk about how this data set was actually created. So it comes actually from our lab. So that all this data was collected right above you, essentially, one floor up. And so it's kind of today's discussion is more kind of like we're actually talking about research that was done recently. So it should be hopefully kind of exciting. All right, so to get into it, so before we talk about the interesting research, just a couple of administrative updates. And then we'll talk, so I'll give a brief introduction to Project 1. It should be quite similar to Project 0 in terms of getting set up with the instructions, the starter code, developing on Google Colab, all the autograder, those things are the same. After that, then we'll talk about this props data set. And then if there's time left over, or as we go along, if people have issues accessing the data set and things, I'm really curious to know because you all will be like the first people to download it and start using it, apart from like myself and the core staff. All right, so administrative announcements. So one slide of them. Okay, Project 1's released, covered that. The autograder, I updated the roster finally. So now if you click the main autograder link on the website up at the upper right, you should be able to like sign in and actually see Project 0, for example, published there. Because I was getting a lot of emails of concern about not being able to access the general autograder, but now it should be there. So if you don't have access to that, then you're probably not enrolled in the class, or email me and I'll try and fix it. Also, the grade scope roster I updated today. So I think you should have been notified by that, but if not, you should click on the grade scope link in the upper right-hand corner of the website and it should take you to our course. And I think you might even see quiz 0 showing up as a future quiz, but if not, quiz 0 will be a future quiz this coming Tuesday. And with quizzes kind of in mind, there's a slight revision to the quiz policy. So this is based on discussion with our collaborating instructor, Professor DeSing at University of Minnesota. What we've decided to do is, because what I described on, I think it was Thursday's lecture, about having the quizzes open at the start of lecture and be open until sometime after lecture, we're going to revise that because we don't want you guys stressed about the quizzes during lecture. So instead, what we're going to do is on days where we have quizzes, which will only be Tuesdays and Thursdays where there's a scheduled lecture, the quiz will open at 7 a.m. So you have, starting at 7 a.m. that day, Eastern time, up until the very start of lecture, so 3 p.m. Eastern, you can take the quiz. There will be like a 15-minute time limit for each quiz. There are going to be one question or two question, intended to be very short quizzes. So once you open the quiz, then the time limit of 15 minutes will start, and you can take the quiz any time of your choosing during the day. If for some reason you have like some circumstances, like you have somehow lecture like all of that day, or you're traveling that day and you don't have internet access or something, we can find arrangements. Just let us know beforehand. That's what we'd ask, like at least 24 hours beforehand, and we'll find a way to handle that. So I included this in the email update just to make sure everyone's on the same page, because I know it's a little bit confusing because I just announced a slightly different policy yesterday. In addition, though, I updated the syllabus with this policy. So hopefully the quiz on Tuesday goes smoothly, and we'll kind of move forward through the semester with this policy. Any questions on these administrative topics, how we're handling the quizzes, if it's unclear, or other administrative questions I can answer at this point? Yeah. What kind of question on the quiz? So there'll be material that's only from previously covered lectures up to that day, and previously graded projects. So if you have an ongoing project, we wouldn't ask material that you would need to have completed that project outside of what was discussed in lecture. So in other words, we're not going to ask implementation details that you would need to finish a project, but we might ask conceptual questions if they were covered in lecture before that day. Does that make sense? All right. Let me ask, have people tried accessing Gradescope now after the update, and have they Does that work? Can you get into the grade scope course? Yeah, okay. And also the autograder, the general autograder site? Okay, great. Okay, so with that then, let's talk about Project One. So today's lab will do a little bit of an introduction to Project One, and then we'll look at the data set that we'll be using for Project One. So the goal of this project is gonna now be where we're starting to build our machine learning models. And in particular, what we're gonna be doing is we're gonna be implementing the k-nearest neighbors classifier, which we talked about on Tuesday this week, and then also 2 linear classifiers. So the linear classifier that's trained with the softmax loss function, and also one trained with the SVM loss function, which we talked about on Thursday. So for the k-nearest neighbors classifier, you have everything, you have all the knowledge you need at this point to actually implement that fully. For the linear softmax and linear SVM models, you could implement them about halfway through, but for training, we're gonna need Tuesday's lecture on optimization before you could kind of finish those. So right now though, if you download the starter code, you could completely finish about half of the assignment, which is the k-nearest neighbors classifier. So in terms of the logistics for this, oh, and I'll mention the slides for today's lecture, or for today's discussion, are up on the website as well, if you want to follow along there. So the logistics for Project One, the instructions are up online, so they're published, so you can see them up under the projects page and then a separate Project One page. We're going to still be using Python, PyTorch, and we recommend Google Colab, but if you prefer local development, that's okay. You will want and need a GPU for this project, so if you don't have a local GPU, then Colab is the resource you should use. The one caveat with this, so if you look on the instructions, the link to the Project One autograder is not yet public, so there's just a couple more kind of details about the autograder for this project that we're ironing out. So expect sometime this weekend that will go online. So don't be concerned that you can't see the autograder yet. That's expected, but it'll go online soon. And this project is due roughly in 2 weeks. So it's next Thursday, or sorry, not next Thursday, 2 Thursdays from now, January 26th at midnight, using the same autograder system. Okay, so if you go to the project website and you look at the instruction page, you'll see something that should look just like this. So just like with Project Zero, we sort of lay out like the high-level goals, which we're talking about now, and then the kind of step-by-step instructions. But at the highest level, it's the same process. So what you'll do is you'll download a zip file, which contains the starter code, where my cursor down here is pointing in the lower section of the page. And then you'll either upload those to Google Colab or start a Jupyter notebook locally, and then implement the features kind of step-by-step as they're laid out in the notebooks. So the recommended flow for development in this project is you would start with the k-nearest neighbors notebook, implement those features, and then move on to the linear classifier notebook and implement those kind of sequentially. That's the suggestion. So within this project, we're going to be doing image classification, right? And the data set that we're going to be using is what we're calling the PROPS data set. So it stands for the Progress Robot Object Perception Samples data set. And it's structured very similar to SciFAR 10, which is a data set that's more widely used in the computer vision community. But the reason why we're choosing this data set for this course is that we want to all start thinking about the objects that our robots will interact with. And so in particular, so Professor Jenkins' lab, the Laboratory for Progress, we specialize in-home manipulation of kind of common household objects by robots. So these would be robots that you might envision for like a domestic service scenario, where you might want them to act on like within a kitchen environment to maybe make breakfast or clean up a kitchen or unload a dishwasher. And so this data set is tailor-made on objects that you would see in that type of a scenario.
Is this like similar to YCB data set?
So yeah, great question. So there's a large-scale object tracking data set called YCB Video, which is what you're referring to. And the specific objects within the YCB Video data set are the same objects within our data set. So within YCB Video, there's Master Chef Can, which is a coffee can. There's a Cheez-It box. There's a sugar box. All of the actual objects themselves, like as a geometry, are the same between YCB Video and ours. The difference then is in the specific labels. So we're not working with pose in this particular data set. And also the background environment in our data set is different than in the YCB Video data set. But it's possible that you could take your models that you're training on this data set and you could directly test them, for example, on the YCB Video data set, if it was a classification setting. And so as we move along, we're actually going to be eventually doing pose estimation with this data set, with with an extension of the classification data set. So you could also apply your algorithms in the future to the original YCP video tracking data set. Yeah. So in this data set that we're working with, so there's 10 discrete categories that we're going to be trying to classify. Each image is 32 by 32 with color art, like red, green, blue color channels, 50,000 training images, and 10,000 test images. And so if you start working on the notebook, so I'll kind of break out of the slideshow here and actually go through this, but maybe I'll briefly just cover it in slides. So if you download the starter code and you upload it to Google Colab, after going through the Google Drive like mount setup code, what you'll see is we load in this data set. And so what should happen when you run the cells below this load the progress objects data set is it will automatically download this file and extract all of the data for you. So if you have any issues with this, like as we're going through discussion today or coming up, please let me know, because I may need to host the data set somewhere else to support the number of students that we have. But as you go through this code, what you'll find is it'll print out first the size of the data set. So what you'll see is the code will automatically reshape the images to be of size. You can see here, so there's a tensor which is 50,000 in the first dimension. So up here, so this training data set has 50,000 images with 3 color channels and then 32 by 32 pixels. Additionally, then we have corresponding 50,000 discrete integer labels to go along with all of those images. And then we have a test set, which is a completely separate set of images of size 10,000 by 3 by 32 by 32, and then 10,000 labels for each of those. So a good first check just to make sure that the data downloads is that you can run this cell, you don't get any errors, and also that the sizes match up. So if the download fails or you get any errors or the sizes don't match up, something went wrong. And you should really let me know, because without the data, you're not going to be able to implement all of the rest of the project. At that point, then, the next cell is kind of a nice feature built into the notebook where it'll actually visualize the data for you. So if you just run the cell, you don't have to implement any code up to this point. It'll visualize the square grid, which is what we've been showing in lectures, right within the notebook for you. So you can see that it should produce in real time. And one thing, though, that kind of the purpose of today's discussion is what we're going to try and answer is, where did this data come from? Because it's really a privilege to be able to work with a data set that's already labeled for us, because labeling data is extremely expensive, right? It's really time consuming if you're a single person and you want to label a large scale data set of, let's say, 60,000 total images. Or alternatively, if you're going to hire other people to do it, that also becomes very expensive. So what we want to talk about in today's discussion is I'm going to describe the process by which this data was actually collected and labeled as a way so that we can start to appreciate the data sets that we're working with, the size of them, and also to think about how it is for the problems that you're interested in. Maybe you're working in a different lab, or you have like an idea for the final project. It's worth thinking about where it is you're going to get the data that you need to actually solve the problems that you're interested in solving. So that's going to be the subject of the rest of the lecture. But the discussion. Before we get into that, though, I do want to sort of walk through that setup code, and I want to just check and make sure that everyone can access the data set as we go along. Because if we run into issues with the data set downloading now, I'd rather solve them tonight versus like a week from now having a lot of people come to me and say that they can't download the data because my server has crashed. So let's step through that. So I'll break out of the slides, and feel free to, for those of you who have a laptop with you, feel free to follow me along in the process. But I'm going to just go through like exactly what you would be doing if you were going to start the project right now. So the first thing we'll do is we'll go to the course website, and we'll go down to the projects page and look for project 1. So within the instructions, read through the instructions, right? Anytime you have a project at the university, always read through all the instructions. But in this case, we find our first step, which is to download the starter code. So if we download the zip file, so it's downloaded, and what we'll then do is we're going to upload it to our drive. So if we unzip the file and then upload it to our Google Drive, we'll have this directory which should be called P1. So let me just rename this. If it's your first time downloading it, it should automatically just be called P1 when you extract the file. And within this, you'll have the notebooks and the Python files where you'll add your implementations to. So So you should start with the k-nearest neighbor Python notebook, so the knn.ipynb file, and then after that move to the linear classifier notebook with a corresponding name. And just as in Project Zero, all the features that you're going to have to implement are going to be in the separate Python files in the root directory. So you won't have to actually change any code within the notebook files to work through this project. You only have to change the code within the Python files. And in fact, as we saw with Project Zero, explicitly do not change the code in the notebook files for the autograder to work. All the code then, you might be wondering, that's within the Rob 599 folder. There's more code this time than what we had in Project Zero. These are just helper functions. So if you're curious about how some of the utilities that are built into the notebook are working, you can certainly inspect these functions and see. The one that is probably I would think the most relevant for this topic today is the dataset that we're using. So this is the code, this project objects dataset Python file is the code that's actually responsible for downloading the dataset, extracting all of the files, and then organizing them for our training. So that's one file. The other file that will be useful, but probably more so once you get a little bit further on into the implementation of the linear classifiers, is the grad.python file, which has some nice error checking utilities for when you're calculating gradients during training. But for now, you don't have to worry about that one. Okay, so let's say we've downloaded our starter code and we've opened up our k-nearest neighbors notebook. Has anyone had issues downloading the starter code? It's been working, right? Okay. Okay, so within this now, so let's say we start to step through the setup code. So we're gonna, once again, like load this, this auto reload module. Once again, just this is useful so that if you change the feature implementations in those Python files, you don't have to restart the notebook or restart the runtime to see those changes propagate. They'll just automatically reload. We'll then mount the Google Drive so we can access the Python files that we need. And at that point then, we can go through the data preprocessing. So the one step here, so you have to specify, just like in Project Zero, the path to this project directory. So in my case, I have this Rob 599 folder, and then I put all of the files into the P1 directory. So this is all the exact same as Project Zero. And for projects 1 and 2 and 3 and 4, this will all stay the same. So at that point then, we get to the data preprocessing. So this is where the data is actually going to get loaded. And so it's really nice, the feature that's baked into this dataset object, which is made to be as convenient as possible, is you just have to run the cell and it'll automatically start downloading the data set and extracting it for you. So I want to pause while mine downloads, and I want, for those of you who have the laptops, to try doing this, and please let me know if it fails. So far, so I see one thumbs up that it's working. Okay, a bunch of thumbs up, cool. Okay, cool.
Sometimes it fails.
Sometimes it fails and not, okay. If you like retry it, yeah. So it sounds like it's generally working. So if it fails, try rerunning it. And if you're, for those of you online, it sounds like it's working. Yes, I have to do a better job checking the chat. Okay, cool. So it's working online. And if for some reason it breaks at some point, please let me know as soon as possible so that I can fix the server. And so yeah, if you want to understand like how that download is actually happening, feel free to dig into the dataset file I mentioned. It was all written for this for these projects. So at that point then, what you should be able to do is just to check and make sure that the data is correct. You can actually visualize these samples as a grid, and you should see the same sort of plots that we've been showing in lecture. So this gets you started. So at that point, if you have the data, you can start actually implementing the project. Okay. So before I go back to the slides and we start to talk about how this data was actually collected, does anyone have any questions about the notebooks, or anyone have any issues apart from the maybe like once in a while sporadic fails of the download? Okay, cool. Okay, so let's go back to the slides. All right, and let's consider now, so we have this data set. It's very convenient, right? We just automatically download it for free. And we have everything we need to train our models, right? We have all these color images taken with somebody else's camera, with somebody else's objects, in somebody else's environment, and we have labels to go with them. But we should really ask ourselves when we're training these machine learning models, where did the data come from? How am I getting access to this data? Because in reality, it's very expensive to actually acquire data. And a lot of the times, like certainly in research, like producing new data sets can itself be publications. Like that itself can be a large contribution to the community. And so it's worth thinking about where we're getting our data sets from so that we can hopefully solve new problems or improve upon the existing approaches that already exist. So the most common way that you would label a data set, and maybe if I asked you to label our data set, so if I gave you all of the images and I said, before we train any machine learning models class, we're all gonna label this data set of 60,000 images. The response might be that you would manually go through one by one, and you would look at the image, and you would try to say, what's the object in the image, right? So you'd take the images, you'd feed them to some human annotator, and hopefully that human annotator would give you correct, like verifiable, trustworthy labels that would go along with each image. The downside with this is it would be pretty slow if you had one person. So more commonly what you would see done if you wanted a large-scale data set is you would sort of crowdsource this to many people, right? So I might crowdsource this to all of you, the students, or we might use like Amazon Turk service to actually like, go through like with many, many humans working in parallel to actually label really large-scale data sets. So this is all possible, and it's commonly used. So a lot of the times what you'll see is, for example, you might download like all of the images on the internet, or all of them that you can afford to store, and then outsource the labeling to human annotators in parallel. The data set that we're working with, though, is actually not done that way. It was collected in a more efficient manner by a few grad students, like I said, who are I think some of them are currently one floor above you. And so today's discussion, I just wanted to kind of talk over how it was that they went through this process. And so this is giving you some like early exposure to a research topic that's actually ongoing within this area. So it should hopefully spur some ideas that you might have for like a final project, or start thinking about some of these questions about how you can collect data efficiently. So the specific research project, the specific paper that was actually used to produce this data is what's called Progress Labeler. And so Xiaotong Chen is another PhD student within Professor Jenkins' lab, and so he led that project. And the overall goal was really to reduce the amount of time needed to generate labels for a set of tasks that are common within the types of problems that a domestic service robot might want to handle. So for things like object classification, pose estimation, and also like image segmentation, this tool is useful for making it easier to collect these sorts of data sets. And so if you're wanting to follow along with or read through the paper, it's linked on the calendar for today's discussion, and also in the PDF, I embedded a link to the paper. So I just want to kind of go through at a high level and share how it was that this data was collected so that we can appreciate what we're working with. So at a high level, this tool works in the following way. So the first idea is, let's say that we collect a video of a scene. So let's say we have a tabletop scene like shown on the far left. We have these YCP video objects, so just like these kind of common household objects on top of the table, organized maybe even a sort of cluttered, in a kind of cluttered configuration. And let's say that we have a camera. So we have this camera, and we're going to sort of move around the table and record a video of just these objects being still on the table. So this is like the far left scene. At that point, what we could do is maybe there's already some very noisy pose estimator algorithm that we could sort of download from offline and try running on our data that we collected. And it's probably going to be very noisy. So what this image on the far left is showing is the initial pose estimates that came from some off-the-shelf pose estimator network, where they're sort of noisy because this is a new environment, right? So maybe that other model was trained on the original YCB video data set, and which didn't have the same backgrounds. It didn't have the same table. But the objects were the same, so we could at least apply it here. At that point, what this tool does, what this paper suggested to do, is you could use a human annotator to, in a relatively cheap amount of time, to sort of correct those noisy pose estimates. And we'll talk about how that's done in a cheap amount of time kind of coming up. But at that point, if you had the pose estimates for the full video, what you would actually be having is for every single frame in the video, you'd have a pose estimate, you would have the object classification if you were to crop out the portion of the image that corresponds to each object, and you would have a segmentation if you were to render the known object model into a 2D plane at the ground truth pose. So those fine-tuned final pose estimates then could be used to train some downstream task, whether it's like a pose estimation network for grasping, or in the case of our class, a classification network, which would try and decide what each kind of sub-image is. And so that's the high-level idea. So it's going to be record a video of the scene, try and use the video in a way where the human would only have to label maybe like a select subset of the frames. So they don't have to label every single frame of the video. We're just going to try and have them label a subset, and then propagate the labels from that subset to all of the video frames so that you have many, 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 many labels, more than what the human originally annotated. Why not use just a single time frame? Yeah, really interesting question. So the reason is that at least if you're trying to use a two-dimensional projection for labeling pose, and so when I say pose, what I'm referring to is it's called, pose refers to position and orientation. So within robotics, or also like computer graphics, we would represent the position and orientation of an object as the XYZ coordinate, so like where, but then also the roll, pitch, yaw of the object. And if we were to label, let's say, the pose of like this object that I'm holding, right, this phone, and then in your vision, or if we were to take an image of how I'm holding it in this position, that image is a 2D projection of an actual 3D shape, right, based on the particular camera parameters that were used to take that camera, or that photo. It turns out that if you try to label some objects using the 2D projection, you actually can get pose labels that are very, very far off, but in the projection, they're correct. So in other words, the 2D projection is in some sense like trying to label 6D pose in a 2D projection is like an underdefined problem. Like there's multiple solutions in the 6D pose space that could produce the same 2D projection. And so that's why labeling a single frame can lead to very noisy pose estimates. So in the video, I think we'll show it coming up, you'll actually see an example of that. So like you might label the pose like actually like a huge translational offset, but it would produce the same segmentation. So instead, if you label the same scene from multiple views, you can correct that like underdefined problem so that you ensure that that your labels are correct. Yeah. All right. So how did they produce this tool that would allow the humans to label more efficiently? So there's this video here which demonstrates a demonstration of the tool actually being used in its full form. So I'll start the video and I'll sort of pause as we go and point out what's happening. So before this video was taken, just imagine that, let's say, like, I'll kind of demonstrate it up here, but for those online, let's say that we have a tabletop scene, there's an object in the scene, and then I was to take a camera just as a human user and just sort of walk around the tabletop taking videos of this object in the scene. At that point, if you convert the video into a set of frames, what this tool does is it lets you load in all of the frames that you just took. So what this user here is doing is loading in all of the frames from some particular data collection. So I'll fast forward a little bit. So these are just color images, but in this case, they also had a depth camera, which would take images, instead of pixels being colors, the pixels correspond to the depth away from the camera of the nearest surface along the ray projected from the camera to that pixel. Later on in the semester, we'll talk about more depth-based neural networks. Yeah, and so in today's lecture, or in today's discussion, like, this is like ongoing research. So it'll give you a flavor. If there's words that are unfamiliar, feel free to stop me and ask, or if there's like concepts that you find interesting, we can have a back and forth, like a discussion about this. So at this point, so they've loaded in the frame. So this is the specific scene then that this user wants to annotate the pose for. So in this case, what's actually being labeled are transparent objects, which are even harder for a human to label, because if you're relying on depth data actually is very noisy for transparent objects, because what happens is, like, this gets into more research, but essentially the depth sensors generally for like commercial off-the-shelf sensors, like what you would see in like a Kinect, like from like an Xbox Kinect, they project an infrared pattern on the scene and then observe how the pattern gets deformed by the shape of the objects in the scene. And for transparent objects, that infrared goes straight through And so it essentially doesn't pick up any depth. So they look invisible. So if a human annotator wanted to use the depth image, they would essentially see an invisible object where they're trying to label. So transparent objects, just know, are even harder to label the pose for than opaque objects. Yeah. Okay, yeah, really interesting question. So the question was, like, if transparent objects are really hard to label, was the tablecloth chosen with this very striking pattern to make it a little bit easier to just maybe detect like the distortions that the transparent objects might cause? I would say, so I have some knowledge of this project. We chose a variety of tablecloths in order to try and capture like a data set that would be representative of many environments that you might see in a tabletop dining table setting. But we did try actually using a pure white, like a pure solid color tablecloth, and we found that the issue was not so much for the human labelers, but the second stage of this pipeline, which tries to reconstruct the overall scene as a geometry, would fail because it wouldn't have enough features to reconstruct the scene. So it wasn't so much the issue of like labeling pose being difficult in the case of a solid tablecloth, but one of these other tools that we need would fail in that case. So in terms of what I'm referring to there, so once we have these images of the scene, you can see like these images cover different viewpoints here, but of the same static scene. At that point, what you can do is you can run an algorithm which is trying to localize the position of the camera over time. So this would be, in this case, it's a SLAM algorithm. So this is orb SLAM running. So what this is trying to do is it's trying to consider how, as the features in pixel space change, it's trying to estimate the pose of the camera. So there's a number of courses here in the robotics department that focus on localization and mapping. So if you're interested in how these techniques work, like Rob 530 would be one, and on the undergrad side, there's another course. But we're not going to go into the detail of how this algorithm works in this course, but for our purposes, the key is that it takes in these image frames, and on the upper left, what it's showing then is a reconstruction of the scene in terms of point cloud. So you can see like this dense covering of points here is the tabletop that it's picking up, and then the blue circle represents the 3D pose, or the 6D pose of the camera over time as it was viewing this scene. And so at that point, once the reconstruction of this scene has been generated, what you can then do is it allows you to render into every single image frame labeled poses, because you know where the rendering should appear in the known poses for each camera at each time step. So to make that a little bit more concrete, so let's say that we've done the full scene reconstruction, and at this point, here's the model of the scene. So we have like this tabletop, which is what has like the highest density of points. And each of those points corresponds to a feature that localization and mapping algorithm was trying to use during its tracking. And now what you can do is you can render, for every single image, you can render the points from 3D space into the 2D image, because you know exactly where that camera was, and you know the camera parameters as an assumed input. But so the key now is we have this 3D knowledge of the overall scene, and we can use that 3D knowledge of the scene to project into the 2D images. There's a lot going on here, so feel free to ask questions. Yeah.
Do you guys use OptiTrack to track the camera position?
We were using OrbSlam. So OrbSlam will automatically track, it'll track the camera position and orientation. So just from the image features. So there's no like external motion capture system. So in some data sets, there are motion capture systems in some of the labs here. Like there are some systems where you'll have like multiple cameras, like at the kind of like the corners of the room, and then maybe you'll use like a fiducial marker or some other way to detect which pixels in each camera correspond to a specific object. But in this case, there's just the one camera that's moving around, and it's tracked, or it's localized using SLAM. Yeah.
Respect to the white tablecloth, so were you able to get results at all using like a mostly white tablecloth or something like that?
Using a mostly white tablecloth, I think that, so let me think. So from what I remember when we were doing those experiments, we could get like some features like off in the edge of the lab, so like up in this room, like if I kind of pause it. So like if we used an all white tablecloth, the problem was we wouldn't get any features on most of the pixels, at least when it's viewing the tabletop scene. But you could still pick up pixels like on the corners of the desks and things like that. But these algorithms, these SLAM algorithms would still fail. So we didn't spend a whole lot of time trying to make it work with that. We instead used like these other tablecloths that would work. Yeah, potentially. Yeah, potentially. That would be, yeah, definitely potentially. It would be good to look at. One of the questions when we were presenting then, so there was a follow-on work where we did try and estimate the pose, the 60 pose of these transparent objects, and that went to an ECCV workshop this past summer. And so one of the question that was brought up there was specifically about the tablecloth color. So the same question that we had today. They were wanting to know, like the community of computer vision researchers was wanting to know, does it work? Does your pose estimation work if there's a solid background? We haven't answered that, so that'd be an interesting final project potentially that we could definitely look at because we have the tools to do it upstairs.
WebSlam really needs like key features.
Right. But it would be interesting to like if you like did like at the like just like maybe 10 like at the kind of like around the table. If you did like even fiducial markers might be like that might be enough for WebSlam. So those are interesting papers, by the way. Yeah, so superglue is like the exact name of paper if you're wanting to look it up. I'll post maybe a follow-up to some of the papers that we referenced today at STEM. Those could work. It would probably depend on what data sets were used for some of those trainings, because a lot of times those are like external, I think, data sets of like external like town squares and buildings. But maybe, yeah. It's good final project ideas coming up. That's what I would say. Yeah, another question. This was using a depth camera. I think the OrbSlam was using a depth camera. Yeah. And then there's a question online, did we use a stereo or a monocular camera? In this project, it's purely a stereo camera. So a monocular it's purely a monocular camera. A stereo camera would be one where you have, instead of one lens, you have two lenses. So like a lot of the modern phones, for example, have multiple lenses on the same device. So at the same time step, they can take multiple pictures from different viewpoints. In this case, though, there's one camera with one lens at each time step. All right. Yeah, so kind of coming back to this approach, let's say that we've run SLAM now on this scene. Right? So we have this 3D scene. We have an estimate of the pose. So all these black kind of like kind of triangular or kind of pyramidal shaped objects, those are representing the estimated pose of the camera at each time step, so the trajectory that the camera takes. So at that point now, we know how to render from this 3D scene into every single 2D image that we've collected. And so what that lets us do for the human annotator to make it easier is if they just select a few of these frames, they can do their labeling in 60 pose space and instantaneously see the projection in multiple viewpoints. So to try and solve that issue of having one viewpoint be an underdefined problem for labeling 60 pose, now what they're doing is they're viewing multiple vantage points of the same scene, and they're going to start trying to label, using a known object model, each of the objects within the 3D space. So to make that like a little bit clearer, I think if I fast forward a little bit. So now what they're doing, so they've imported now a known object model. So this is basically a collection of vertices that represent the actual known structure, like the known geometry of this, in this case it's a mug. And so now what you're seeing, so let me pause this here. So what you're seeing is a few things. So in the lower right-hand quadrant of this visualization, that's the 3D scene. And then the orange, the small orange kind of shape within that is, it's once again a projection, but that's an orthographic projection. But so that's a projection of this, the pose of this object in the 3D space. In the other three views then, so like the upper left quadrant, the bottom left, and the upper right, those are the projection of this labeled pose for this specific object, which is highlighted in orange, into the actual ground truth RGB images that were collected. So now what the human can do is they can use their own like visual, understanding of space to try and label the 6D pose, the 6DOF pose, and see the corresponding 2D projections in multiple viewpoints in real time. And so what you'll find if you kind of study this video, and it's linked in the slides if you want to see the YouTube of it or go through it at a different pace, is as they move it in one axis, it seems like it should fix the projection in all of them, but it doesn't. It's still challenging to actually label. And so you can imagine if you had to label the 6D pose using only one viewpoint, a lot of the times you will label incorrectly because you'll happen to sort of try and solve that underdefined problem incorrectly. And in addition, the other key thing to take away from this is that at this point, they're getting more confident about their pose label in the 6DOF space, but they've only been looking at 3 viewpoints. But the fact that they're confident and it seems like they're correct implies that you could propagate that 6DOF pose label to now all of the, let's say, hundreds or thousands of frames from the overall video because the pose is staying the same. So now what we would have from this overall process is we would have the known category for that portion of the image chip if we were to take any of these images and just isolate it on the, let's say, like a bounding box around where the object model is projected into. So that's how our classification data set is going to get generated. We also, though, have the 6D pose for eventually every object in this scene, in every frame. And then also we could have the segmentation because we could just render the, instead of like rendering a bounding box, you could render an actual like pixel-wise segmentation for every object based on the 6D pose and the known camera viewpoints. And so that's a way of making labeling like this many frames from this overall video much cheaper to do because you're only having to really use like a few viewpoints to actually do it. Mm-hmm.
Here you're using like 3 different perspectives of the camera to properly align yourself, right?
Mm-hmm.
So is there like any metric to say that for other 1,000 images, the point clouds matched exactly the original one?
So say that again. So the point clouds? Do you mean like
How do you verify that same thing worked for the other 1,000 images? Like how do you probably?
So in some sense you have to have, so at some point it becomes up to the human labeler to say, I'm confident that I've labeled this correctly. The same way if you were going to outsource labeling of just the images without just classifying the images, you also have to trust that your labelers are labeling correctly. So a source of noise is if you have labelers that are like sloppy or they're intentionally maybe giving you the wrong labels, like they're trying to poison your data set. That's kind of a whole area. So it kind of comes down to trust. You have to trust that your labelers, your annotators are incentivized to give you the correct labels and that they're doing a thorough job. But yeah, at the end of the day, all of these data sets, they come down to, at some point, a human had to sort of sign off and say, yes, this is these are the labels that we want to learn from. So another question in the back.
Just to summarize, just to make sure like
Mm-hmm.
I'm on the same page. To label this data, you need to create a CAD model of the exact dimension and then have a good SLAM algorithm to run around so we can capture the whole thing and get this understanding of the scenario, all the dimensions, and then try to match the CAD model to the object, and then rest of it is done by the software because it knows what is it because of SLAM and other positions.
Yep, exactly. So to summarize that question, so the kind of key assumptions are we have only known objects within the scene that we're trying to label. We have an object model or a CAD file or an OBJ file to go with each of those known objects. We have rendering software that can render those corresponding objects. And then we have an RGBD camera, so like a color and depth camera that with known camera intrinsic parameters that we can use to collect the images. And then a SLAM algorithm and an environment that's conducive to SLAM functioning to actually estimate the poses of the cameras. So yeah, those are the core assumptions. Mm-hmm.
Classification, whether it's a dog or a cat, but here, how does the label look like?
Right. So like the highest fidelity label so the data set we're working with is obviously a downsampled, like classification version of this data. So the highest fidelity labels that come out from this are, so you have 6.pose, which is going to be like a dual quaternion, or maybe like an XYZ and then a quaternion. So you have that. You have the corresponding category that is associated with that specific pose label. You have the you have a specific time step for which frame that label corresponds to. You would have, I think those would be the main ones. But from those high fidelity labels, you could derive a bounding box, which is how we're extracting the image chips in our subsampled version, the props data set. You have obviously the discrete category because you know what the object model is and what the category for that object model is. So you have, so that could be a classification then data set, which is exactly how props is created. But in addition, because you have the object model and all of those other like intrinsic parameters with cameras and so forth, you could render those poses into a segmentation. So like a 2D segmentation mask, you could train like mask RCNN or some other segmentation model. And I suppose to some extent, assuming that you had the CAD files as input, you could also treat those as labels for if you were to try to like, there's a whole area of work trying to estimate a CAD file from an image, like try and estimate the object geometry given just pixels. So that could be another label, but in this case, we're assuming that that's already given to us. So, and then there was a question online: do we account for spatial drift due to the use of OrbSlam? In this project, so I would suggest if you have like more specific questions about this, Xiaotong Chen is within our lab. So you can find his email on our lab's website if you want to ask him follow-up questions. From what I remember, OrbSlam was extremely effective, and we didn't observe like any side effects from drift. So if there was drift, it was small enough that it didn't affect our renderings based on error in the estimated pose. Yeah, and so I think we're out of time. I'll stick around to answer any more questions. But now that we've seen like how much work goes into kind of creating these data sets, or just the tools to label them, hopefully now we have like a better appreciation for Project One and all of our future machine learning endeavors to really treasure the data that we're using, because it's expensive and powerful. And then, yes, we have a lecture next Tuesday, so I'll see you next Tuesday.